Welcome back to Refactoring Paleo. My name's Tom. In this episode, we're working on moving SQLite Part 3, SQLite Backup. If you remember from last time, I said that the application seemed to have worked, but I wasn't quite sure, so I was going to do some unit testing before this episode. Now, a couple of notes. For the unit testing from this point on, whenever possible, I'm going to be using Swift testing, which is Apple's new unit testing framework. This is sort of a replacement for Xcode. And the reason why I say sort of is because it doesn't fully do everything quite yet. So Xcode is still required for some things, but Swift testing can handle a lot of it. So as of right now, there are 29 unique tests in my test suite, including both the application and the module. But there are actually 168 test runs, which means there's truly, in an old style, more like 168 tests rather than 29. The reason why there's a difference there, in Swift testing, you can use parameterized tests where you can actually set up values you want to test in a series of parameters. Instead of having unit tests where you loop through things or just have a bunch of tests testing slightly different variations of those values, you can now just pass them in as parameters and you can just have one test and just have everything go through that one test. So that speeds things up. It simplifies writing the code. As of right now, the main application has only got about 11% code coverage, which is probably slightly better than it was. And our module is somewhere around 90. Again, code coverage doesn't necessarily mean you sufficiently tested. It just means a statistical measure of how much you tested. So what did I find? Well, I found out the code only sort of worked. It would have shown up as bugs much later on down the road. And it would have been hard to debug without the presence of those unit tests. So every time I do unit tests, I always find there was a lot of little changes I made, but I just want to highlight a couple. And one of them is that my codable library only handled a narrow range of expected. It turns out there were a lot more types that I needed to handle in a lot of different ways. For example, I didn't handle NS number sufficiently. In the process of writing these tests, and these particularly parameterized tests, I found that the code did not handle binding values in particular for the SQLite calls to be sufficient. So a lot of those tests were built around that part of the code. And one of the other things I started to notice is that I wrote some things in bad ways that made some code untestable. For example, passing in SQLite pointers as optionals. That's not a good idea. What I would have to do at the beginning of the function is to unwrap that with a guard, and if it failed, I would have to then return a failure. And that's not great. What I should have been doing was require an unwrapped value from the beginning, and whoever calls it should have the burden of unwrapping. So that reduced a bit of untestable code. There was also some other refactors where there was some similarity of code that could not be tested that I pulled out. And part of the reason why there's untestable code in that library is that it's very hard to mock out SQLite itself. So I'm actually doing some integration tests where I'm actually calling SQLite code directly and actually getting a response from SQLite. But there are a few cases where it's very hard to set up, like forcing SQLite to have an error. That can be a little bit tricky to do. So a lot of that code is untestable. Some of it I can pull out into a separate little function and test that. For the most part, we want to get rid of untestable code as we can. As part of that untestable code problem, we have some pending changes that I need to do. For example, using composition for table representable. If you remember, table representable is a protocol that I can attach to a type to make that type essentially a codable version of a table. So I can actually do a query and take those results and just put them in one of these table representable types. The problem is not all table representable types are all going to do all the basic CRUD stuff, like create, read, update, delete, those sorts of things. Some of them are only going to read. Some will create. Some will update. Right now, table representable does all of those things, but it is not the best thing in the world because, for example, I'm having to either write unit tests for code that doesn't do anything to get code coverage, which I didn't do, which is why I'm only at 90%, or I can use composition, having protocols that define whether or not it can create a table or another one that allows you to update the table and so on. So I need to actually increase the use of composition for table representable. And I found out that a lot of the function names I came up with, I kind of knew weren't great when I wrote them, but I'm going to have to rewrite them. I didn't actually do it yet, but over time I'm going to be changing some of these things out. I may or not bring it up in the videos, but there's going to be some functions that are going to get read. Okay, let's move on. SQLite Backup. SQLite Backup is a tool that's in SQLite that allows you to load data and save data from in-memory data. So in Payload Rows, what we're doing is that since we have an in-memory SQLite store, we want to save that to disk as our document file, and then we want to read it from disk when we open that document. It's its primary job. Whenever you open a document, save a document, we're going to use SQLite Backup. And right now, it currently lives in our main NS document class. So just to give you a little bit of detail about how SQLite Backup works, it's very simple. You have your in-memory store, you have a document file somewhere, a SQLite file. So you need pointers for both. You need a pointer for the in-memory, pointer for the file. Once you have those two things, you can call SQLite Backup to generate a third pointer that's going to represent the backup process. Once you have that, you can actually step through the process of paging data from one to the other. You can either control that by doing your own steps or let SQLite handle that yourself, and that's what we're going to do in this case. We're going to let SQLite handle that itself. And then once that's complete, we can do a finish that will actually put everything into place, and then we're done. So this is our example code that is in our document right now. We create a source file or open a source file. Check to see if we get a okay back from there. We do our init, do the backup using this -1 value to say that we're going to want SQLite to handle the paging. And then when that's done, we do the finish. Writing the file is just the opposite. Here, we just swap which pointer is which. And then we go through the process, the same process, and be done. And this brings up something so simple that this code is almost exactly the same. If you go back here, there's almost no difference between the code. That's an example of don't repeat yourself. Same code. All we need to do is swap what pointers we're using. So this code in the middle should have been just used once, but we're using it twice. So I consider this the old but simple way. It's all done in an NS document in two methods. It's very simple. And it's not necessarily wrong either. Being simple isn't necessarily. But in this case, there are some issues. First of all, does the document itself need to know how this works? You can make an argument that it doesn't really matter, but one of the reasons this app is hard to deal with is because how tightly integrated SQLite is into the application as a whole. And this is an example of it. This means that we have a tight coupling between our document and SQLite. And that's what we don't want. We want to keep the SQLite code off on its own thing, doing its own thing. Because eventually we're going to have to start dealing with the reality that we need to be able to open old file formats. We're going to have new versions of the file formats in the future. And that's going to really start cluttering up the NS document. So we want to move this somewhere else. That makes a bit more sense. But that leaves that the document does have a role in this, and that is it is the trigger for reading and writing the file operations. So it's got to communicate out and pass in what document paths there are so we know what to do. So what's going to be the new way? And it's definitely going to be less simple. In this case, all direct SQLite code should live on our model. It shouldn't be scattered around everywhere. It should just be one very clear cut. Our document should tell our document model to read and write the data. Now, where it goes from there, though, is a little bit more hazy. We can either have the document model do the rewrites, or we can actually have the in-memory model to do so. Or we can come up with other types that are meant to just handle reading and writing the memory. And we may have to do that in the future as we start versioning the database, or if we change out the database format. So we have to have it in a way that we can pull that out relatively simply without having to do a lot of work elsewhere. Now, one of the other things that happens in the document whenever we do the saving is that there are method calls to update the database before we make changes, particularly when you're writing the database. So it's going to tell different parts of the model, essentially, to update the database. That will probably leave alone at this point, but eventually all that's going to be handled differently. So we're going to have to be careful about how we integrate this. So that's something to be cautious that we don't break at the moment. So let's get started. The first step I'm going to take is to answer this question. Can we even access a SQLite file that's on disk? Now, the app doesn't actually read or write directly from a SQLite file, but we must be able to open or create those files to be able to do the backup. Either if we want to read it, we have to open up, get the pointer, and send it up to the backup function. So we need the ability to at least open and close files on disk. For testing purposes, we at the very least need to read and write, or at least read from that file on disk. We don't really necessarily do any writing directly right now, but we may do so in the future, but we need to at least be able to read from it. It is possible in the future that we may need to also validate the file, that it is indeed a SQLite file, and what version the contents of the file actually is. Right now, there's no versioning in our system, which is actually a weakness to the current system. So we need to be able to find out what the correct version of the file is. But right now, that's what I would consider a YAGNI, because it's not something we're doing. So remember, a YAGNI is you ain't going to need it. So we have to treat that as a YAGNI. We're not going to touch it right now, but we want to keep it in the back of our minds. So we'll also need a sample SQLite file to set up our integration testing. So let's do this work first. So here we are in Xcode. And as you can see down here, I have created our SQLite file. It's just a simple file. It's got one table, and that table is built up of items that represent this testable table type. So we're going to use this for integration testing. Now I have some integration testing already set up. This is some of the work that I've done previously. And right now we're broken because I've kind of stepped back the work just to go through the process of showing you what I had to do. So here's our first test to see if we can actually open and then close a SQLite file on disk. I wrote a convenience method up here, which is throwing an error, that basically finds our bundle, finds the path to our SQLite file, and then if it all opens correctly, we attempt to open the database and return our opaque pointer. Notice that it is not an optional pointer. So if we are successful in opening this file, we should just get a pointer that won't be optional. If this fails, it will throw. In Swift testing, throwing is kind of the normal thing to fail a test in some ways. We're going to need these functions. We already have this one in our SQLite interface, but we don't have this one up here, which is Open Database. So if you're wondering what this SUT is here, it means system under test. So I used to use test object for our object that we're testing, but now that we're focusing more on structs and other things, I've adopted the SUT or SUT, system under test approach. So right now this function doesn't seem to exist there. And if I built it, this would also show that it doesn't exist. So since we're testing this SQLite interface, let's open this on the right side. So you can see I've already written the Open Database function. So let's put that back and start asking questions. So this function starts off with a variable for the opaque pointer. We go through the process of SQLite Open version 2, and we're opening it as a read-write, and if it doesn't exist, create it. Now in the future, we may not want to always do this. We can make some changes to that in the future, but as of right now, this is what the app is doing. So I'm going to go with it. And of course, if this successfully opens, the variable will be set here. Now, if this open command will fail for some reason, I have this function that will check the status and throw if it's failed. So we won't go beyond this. Now it is possible for this, since this is an optional pointer, that this is still going to be nil, even if it gets passed here. So we want to unwrap that. And so if it fails to unwrap, then we throw again. So this piece of code is going to be really, really hard to do. So I'm just going to assume that I can't test that one directly. And then finally, if we're all successful all the way to there, we return the store as a regular thing. It's not going to be an optional. Okay, so let's see if we can actually run this test and see if it works. Test succeeded. Now, of course, I didn't turn off the disable feature, so now it's enabled. Let's try that again. Let's run it. Okay, that time it passed. So we now know we can open and close a file on disk using our SQLite interface. Now, one thing we want to make sure we are not doing is that we're not going to be testing SQLite itself. SQLite is an established library. It has its own set of tests, and we're not actually testing SQLite. We're testing the interface that we set up for it. So if our interface is working, then it should be doing the right thing. So we're not really testing SQLite code, we're testing our interface. Now this next test here, I'll go ahead and enable that one. Doesn't require us to make any changes over here because now we're going to say, okay, if we open this file, we should be able to see the contents of that file and be able to read it. Now, why am I doing that? Well, it is possible, and matter of fact, when I was doing this, I ran into this very problem, that we opened the wrong file and we're not doing the right thing in the test. So we want to be able to open the file, the correct one, read all the data, and make sure it's equal to an expected set of data. So if we look up here, we can see this array of testable table items. So each one of these items should exist in the database. So let's see if that's correct. So we've enabled this test. We're reading the data from disk. We're opening the file. We're going to use an execute codable query. So all we need for that is the file pointer and the query. And this is one of the things I mentioned earlier. I don't like the name of it for the stored values. I want to replace this with something a little bit better. But if we actually do not get an error from here, we're not going to throw, and therefore we can move forward. But what this will do is it will query this table that's on the SQLite file and automatically convert those to testable table items. Then for the sake of safety check, I want to make sure that we have 3 items because that's all we have in the database. And then we expect that the items are actually equal to the items I have up above. And then at the end, I want to close them. Now, I might want to change this, though, to defer, to do this to defer when we want to close it all the time. So I might actually move this somewhere else. But for right now, it's fine. So let's run this and see if it passes. Okay, it passed. Now, just to prove to you that it will fail if the data table that I expected to have is wrong, let's change something up here. Let's change this to 28. Remember that is 20, actually 23. Change it to 28. Let's see if it fails. Indeed, it fails. So if you're wondering what that was, in my breakpoints, I have test failures turned on or turn those off. I find it's very useful to debug at times to be able to do that. So it's definitely failing if the values are wrong. Okay. Let's make sure that it's correct this time. Okay, so this function is testing. You can see that I can't get into this code that I didn't expect to get into. So that's going to increase our tested code, but we did get the testing here. So we know this code is now working. The next step is to actually do the backup from disk into the in-memory store. That's going to involve a couple steps. We have to open the in-memory store. We also have to open the file on disk, execute that backup, and then close the file. Now we also need to do the opposite, where we have in-memory store we want to save to disk. That will require some differences. One is we have to create the stores as before, but we'll have to do a little extra work because we're not using a prefabricated table. We actually have to create the table in the database and then populate that table and then execute the backup and then close it all down again. So let's look at the tests I wrote for this and the code that's going to do the backup. On the left, of course, we have the unit tests. On the right, we have the code. This gets a little complicated because there's one of the things we want to make sure is that we want to shut down all the open databases. It might probably be fine if we don't, but we want to make sure we clean up things properly. Going through this test, we want to open up the file on disk, create the in-memory store. So it's going to be very similar on going both ways. And so right now in this test, we're going from disk to memory. So we have both of our stores. The file itself will have the table already. So now, since we have both of our pointers to the different stores, we can then execute the backup. Once we execute that backup, we can verify that it has the right content. First, we can check to see the original file matches up with what we expect to be there, just in case something has changed. And then we can check to make sure the copied items, the stuff that was in the in-memory store, actually also matches the array of expected value. And then for a final check, we can make sure that those things are all equal. But if we look at our code now, we'll see that's actually pretty simple. We're doing a backup where we're asking for the source pointer and the destination pointer. We run the backup. We make sure that we have the pointer. We basically want to unwrap that. That's actually optional. We want to unwrap it. It probably won't fail, but it might. So it's going to be hard to test this piece of code. But we also threw in a defer. Whatever what happens at this point, we want to make sure we call backup thing. So the next line is actual do the backup step. So when that is finished, we expect a good result to come back. And once that good result comes back, we will execute finish. But if it does throw, we'll also execute finish because we want to clean all that up. Let's take a look at how this fares. Okay, the test passed. Now I will say both the tests I'm going to show you, like all the other tests, did not pass the first time. I built this up line by line and built up the backup. So I'm kind of skipping over a lot of test failures and ended up with a successful test. Now that was a pretty simple operation, going from disk to in-memory. It's a little bit more complicated to go the other way because the in-memory store will always be empty. And if the in-memory store is empty and you try to do a backup, it's not going to work quite right, which is something I had to work through. So this test is very similar, but it had to add a few extra steps. One, we had to create a temporary directory with a temporary file, create a path for that temporary file, and then we had to create it. Before we create it, though, we wanted to add a defer. Probably what I should do is move this down one line. So now, if this is successful in creating the path, the database, we can then make sure that we defer to clean it up. If it fails, we don't have to clean anything up. Same is true here. Actually, let me put this back up. These are two separate defers. So this one is deferring since we created the file, created the database, that we then remove it. This one will say, okay, well, we also need to make sure we close it. So I think this one should actually go ahead on the first one. And I could probably wrap these two together. And come to think of it, that's probably a good idea. So let's do that. Close and then remove it. I'll save this a few lines of code. Okay, so we are now open the file. Once we finish the run, it will close and remove it. Even if there's an exception, it will still do this. And at the end of this, we're also going to say, hey, let's make sure that file exists. Okay, next, we have to create the in-memory store. The in-memory store is a little bit more complicated. Again, we want to close at the end of this run. So once we create it, we want to have a matching close. But here we actually have to create the table because it's an empty database. So we create the table using execute query and just do a create table query on that. So that will create the table in the database. We want to set up an insert query where we're actually going to take the bindings of all the data and bind them together and put those in the query. And once we have that, we then populate the database with those values. Okay, so now we're ready to do the actual thing, and that's the backup. So our in-memory store has a table in it, and we have created the destination file. So once this function is done, we should be able to access the items in the file and in the store. I should probably change these names around because they are now different. Actually, I want to change that a little faster. So the copied items are now in the file, and the store are the original items. So now we have the same expect down there. We should see an equivalent between the original items and the copied items, and make sure the copied items still match the expected table. That is a long test. Build succeeded. Test succeeded. Let's make sure we haven't done anything else to any part of the other system. Test succeed. And again, we have a spot here that I cannot check because I cannot fake this particular error. But I have to be prepared for it. Next up, we want to be able to call our backup function. The question is, where should that be, of course? Right now, what we're trying to get rid of is all this backup is being done in the document. We really don't want it there. It kind of makes sense that it goes with the document, but we want somebody else to manage that. The document can hold on to whoever manages that, but again, the document doesn't necessarily need to manage it itself. Realistically, our in-memory store type should be the one to actually do the loading and saving of the memory store. So that means we need at least a load function and a save function. So let's go to the code. Okay, I've done pretty much all the work inside the memory store. So I'm not going to bother talking about tests at this point. We've spent a lot of time on tests in the last section, but I just want to go through my solution in the in-memory store. One of the things I quickly found is that I wanted an access to the SQL pointer that would automatically unwrap it. I don't know how much longer that's going to be here because right now I have to keep the SQLite pointer as an optional. But I don't want to be accessing it as an optional all the time because then, therefore, I have to do the unwrapping everywhere. So I've decided to put it in one place so we only have to do it once. So we have our load function that will call into backup, and we have a save function that will call into backup, which is this function here. So this backup uses this type called the backup info, which is a very simple type up here. So it has a path, and a type. So whether or not it's to or from disk. So I only really need this code once and just be able to read the backup info to know what to do. So these two functions, load and save, just create a backup info that tells what path and whether or not I want to write to it or read from it. And then this code does that. And I also did some modification to close file, so you can just call in here and close the file. And that's all that's really necessary. And that leads us to our final step, piping these calls from the document to ultimately to the store on disk. Remember that the document actually receives the notifications that it needs to load or save document data. So we have to be doing something in the document. If the document gets one of these commands to load or save, it needs to pass that message along to trigger the save or load. In other words, it has to talk to the document model because that's its path to get to the memory store. The document model will then pass that message to the memory store, and it will either load or save it. That's a really quite simple approach. But there are a lot of things that need to happen sooner or later. First, we have to make sure that all the data store is up to date before saving. We're not going to do that now because we're not really doing that anyway, right? Just yet. And of course, the data store, the in-memory store itself is not particularly useful data types in there. We have to be able to convert those types into something useful for the application. And we're going to have to do that as well, but we're not going to do it yet. So right now we're just storing and reading the data from disk. But eventually we're going to have to replace how we change those data in the database into something that is a useful type. So we're going to have to figure out where that moves, but we're not going to deal with that yet, but just something we need to consider in the future. So let's wrap this up real quick. So here we are in the document model. We have a write to file and read from file. Those two methods just call into the in-memory store and tell it to save and load. We saw those functions before. We just pass in the path and it knows what to do. But somebody has to call the document model. So that means we need to go to the document itself. Okay, on the left here is the new code, on the right is the old code for comparison. So on the left, we're doing slightly more in the read from URL than we were before, because we have a separate function that does all the SQLite code, which is the read to memory store to path, which is kind of a really awkward name, but we have this function here that simply we tell it what file we're going to read from and what error to capture, and if there's an error, we log it. Eventually, we're going to need to change that into a notification for the user that it can't read that, but right now it's not. Similarly, for write, we do a few things to set up, and then we just have this simple write store. And then we also get rid of this whole function, write in memory store to path. So again, we pull the data in, set up the document model to write, and then check for an error. Now there's a few weird things still going on. We're still passing around the pointer to the document store to various different types. But that's kind of beyond what we're trying to do right now. We're trying to get rid of the actual SQLite calls out of the document. And so in terms of reading and writing in memory store, we've accomplished that. But we got a long ways to go yet in trying to clean out the SQLite stuff out of the NS document class. In particular, we will have 3 more methods in the document class that directly interact with SQLite. And it's time for us to start getting rid of those out of the document type itself. So next time, that's what we'll do. My name is Tom. Have any questions? If you have any comments, leave them below. And I hope you enjoyed this episode. Thank you.